after 4 weeks. Excellent lecture from the group. I want to talk about spin liquids, and particularly from a fermionic point of view. So this is what I plan to do. I'll start with an introduction to the notion of spin liquid. I know that you have had at least 2 lectures on related subjects from Ashwin, talked about frustrated magnet and Matthew Fisher. I try not to repeat too much, but with a little introduction. And the emphasis is on the notion of emergence. That these spin liquids are interesting not just because they don't order, but because they don't order, they're associated with it many interesting properties. And we expect that new particles and new gauge fields would emerge at that moment. That would be the discovery of these particles will be the really exciting things that we hope will happen with these materials. I will spend most of my time describing spin liquid in one particular material, this organic compound, which is the best study of these candidates we have. Basically, 3 classes of candidates. The organics are, I think, has been studied. There's the most data on it. They're very clean, and I think they're most promising. And there's still a lot of open questions which I want to expose to you. We don't pretend that we understand really what's happening here. It's just, I think it's the proverbial tip of the iceberg. What we see. Then I want to describe effective field theory that we think describe these spin liquid. It's essentially some kind of fermion coupled to a U1 gauge field, very much like the world we live in, which is electrons coupled to the electromagnetic field, with some differences. And one of the differences is that this gauge field is in 2 dimensions, whereas the gauge field is in 3 dimensions, even though the electrons are in 2 dimensions. But that turns out to be a big difference. And so there's a lot of questions about whether this is actually an example of non-Fermi liquid. So, again, the notion of non-Fermi liquid is a very popular one. People want to find examples of things that violate Landau's criterion. And this is a field theory by itself. It's very interesting because it shows signs of violation of Landau's criterion. And I want to describe to what extent is it or is it not a non-Fermi liquid. Then I'll go into a little bit more about the experiment. And the experiment seems to call for something a little bit more complicated, that this Fermi surface may actually be unstable with further instability. And one possible instability is actually that these Fermi surfaces actually start to tear and form a superfluid. And the question is, are there more experiments you can do to probe such a thing? And I think the big question facing us is there any way to detect the gauge field if they exist? I think up to now there's certainly no direct evidence. And I think that's one of the things that I'd like to think about, whether there's any experiment we can suggest for people to look with it. So I think one theme of certainly my research is to think of ways of probing these materials and applying experiments and encourage experimentalists to go look for them. And so I encourage anyone who's interested to join this endeavor. I think there are many open questions. And then I would talk a little bit about the other 2 classes, which are the cargonate and the hypercargonate, which is in 3 dimensions. And in the end, talk a little bit about doping the spin liquid to make them a connection to high temperature superconductivity. Okay, so that's the menu. Well, as you know, the antiferromagnetism is kind of like second nature to us physicists nowadays. We call this the Néel order state, Néel, but maybe not too many of you know that this Nobel Prize-winning paper was actually a theoretical paper. It's essentially a mean field theory extension of Weiss's theory for magnetism to antiferromagnetism. And it took, 20 years before this state was directly seen experimentally. Of course, in between there are various experimental. I think think initially he was inspired to explain some uniform susceptibility. You know, the anti-ferromagnetic, of course, we now know there's a kink in the susceptibility, and he was motivated to explain those things. And we associate anti-ferromagnet now with local moments. Right? These local moments can form with strong correlation. One way is the Bond transition, one is the spin becomes localized. And because of virtual hopping, you have an anti-ferromagnetic exchange. So this is well known to you. In the public lecture, I mentioned that the history of this anti-ferromagnetism is actually quite surprising in hindsight, that Néel was actually quite viciously attacked over several years by famous people for harboring such thoughts. And so, in today's language, I think the doubt can be cast in the following way. See, Néel's picture is essentially a classic one. Up, down, up, down, up, down. Unlike a ferromagnet, in the case of a ferromagnet, if all the spins are up, then you can show that that is an exact ground state of the Heisenberg Hamiltonian. But if you have anti-ferromagnet, if you take the state, if you hit this with the Heisenberg Hamiltonian has a mutual spin filter, right? The x and y term can be written as a mutual spin flip. And so if you hit this state with Hamiltonian, then you will convert this down to up down. Right? So that proves that this is not an eigenstate. It cannot be a quantum mechanical eigenstate. So to make matter worse, if you keep hitting it with Hamiltonian, you're supposed to project into the true ground state, and then you start scrambling this spin structure. So that's why quantum mechanical. So these, if you hit with Hamiltonian, we can understand that it's the state that you generate is a quantum mechanical fluctuation, zero-point fluctuation. And so we know that there should be a lot of zero-point fluctuation which scramble the spin. The question is that fluctuation strong enough to completely destroy this order? So in the absence of any experiment or any good theory, there's really no good reason to accept.
I guess it was also back in those days that it was proved that the ground state is a singlet, which added to the confusion.
Yeah, perhaps, yeah. And there was this famous exact solution by Bethe, which is already in the 1930s. Probably Landau knew about that. And that exact solution doesn't have any Lagrange order, precisely because it's killed by quantum fluctuation. So it's amazing that people in very early days immediately came up with the notion of quantum fluctuations. Start asking a very deep question, anti-ferromagnetism. Yeah. Well, of course, history tells us that Néel has the last laugh because he's been proven right experimentally. Right? So the Néel state turns out to be a very robust ground state in both 2 and 3 dimensions. The only exception we know are one-dimensional chains nowadays. And so basically, until recently, all states that have anti-ferromagnetic exchange ultimately find some way of ordering. Now, if they're disordered, it could form a glassy state, form spin glass state, which is an entirely different field of study. But that's not what I mean by spin liquid. So I want to leave out glassy, which is a situation where you have many ground states separated by energy barriers. So,
I was going to say, I mean, it seems like that's a feature of almost any broken symmetry state. That unless the Hamiltonian is trivial, there's some non-commuting operators,
right.
combination non-commuting operators.
That's right.
If you have long-range order or even just broken symmetry state, then
Yeah.
some terms will
That's
shuffle you around,
Yeah.
right?
Yeah. So the question is there a small parameter that controls this? In superconductivity, of course, there's a very good small parameter, the ratio of the phonon energy to Fermi energy. But in the case of spin, there is no small parameter. And the same goes with critical phenomena. Critical fluctuations, there's nothing to control these fluctuations. Okay, but in hindsight, people have done large spin expansion, so on and so forth, and somehow it works down to the spin equal to 1/2, right? In textbooks, we've done spin wave expansion, which is semi-classical, and you put s equal to 1/2, and you get very good value of the ordered moment. So nail that down. Okay. Now, I think Anderson was the next person who raised this kind of thought about quantum fluctuations, and he introduced the notion about what's the rate of greatest volume. He was asking the question whether, with frustration, the triangle, the triangle, he was thinking of a triangle, a lattice, which is frustrated. Right? So, of course, he understood that the best chance of defeating the air was to go to a frustrated lattice where the classical energy is small. So, so his key idea is that spin singlet can give you a better energy than anti-gravitational orbit, and especially spin a half is the most quantum mechanical of all spins. Right? So spin a half is way the best chance of defeating the air. So this idea can be seen very easily from an example of one-dimensional chain. So if I have a one-dimensional Heisenberg chain, I can write down two kinds of trial wave function. Right? I can write down the Néel trial wave function, up, down, down, and just calculate its energy. The energy will be 1/4 J per bond. It's a spin a half. For each bond, I gain 1/4 J. Now, another trial wave function, which looks rather stupid at first, is it just forms singlets. I can lay down singlet, and so this breaks translational symmetry, just like this. But so the singlet is just the quantum mechanical combination. You remember that the energy per singlet is S plus 1 times J. That's the energy gain. Now we have to be fair, we have to divide by 2 because you don't gain anything here. So per bond is half S plus 1. And again, 1 is quantum mechanics. Right? So this is why for a spin a half, this 1 is actually dominant. So that's the key. Right? So both energy gains come from 1. So when you work this out, it turns out that you gain 3/8 of J per.
This is negative, right?
Negative, that's the energy gain. 3/8 per bond. So 3/8 is bigger than 1/4. Last time I checked. So so therefore, without doing anything, this is already a better trial state for than the other state. And then of course now you can start mixing them. Right? You can imagine making linear superposition. Well, this thing breaks translational symmetry, which is not good, so we can mix in another piece or have longer bonds and so on. Right? So this energy is already, I think the exact state is what, 0.43 or something. But this is actually not so bad. And actually today we understand Bether's exact solution as indeed as a linear superposition of these singlet, but with long range over long distances. Okay. Now this same argument says that your best chance of defeating the AL is in lower dimension, right? Because if you go to higher dimension, then this counting doesn't change. Per bond is the same. But this one, you get more neighbors. Right? So in 3 dimension, then I think this one, if you go to a cubic lattice, you have 3 times this. Right? In 2 dimension, you have 1/2. And so 2 dimension square, this is marginally bigger, so that's already some possibility of play around. One side remark is that honeycomb lattice is actually an interesting case. We usually think of honeycomb because it has 2 AB sublattice. This is ideal for making anti-ferromagnet. Drop down. Okay? But in fact, this is kind of between 1 and 2, between chain and square, because this thing only has 3 niches. So if you do the same calculation, you get exactly, I think, 3/8 per bond. So the honeycomb is actually where this naive antiferromagnet and the naive singlet are at the same energy. So some of you may know that from the Lang's work and that's what they found recently very interesting possibility of spin liquid in a honeycomb lab is nearly no transition. So so maybe we don't need frustration to stabilize this spin liquid. We just need a few neighbors, right? So to defeat this yeah. Okay, that's on the side. Okay, so starting from that, then of course the notion of resonating valence bond is to make linear superposition of all kinds of covering. Here I've drawn only nearest neighbor covering. This would give you an energy gap, but in general, we can imagine having very long distance singlet bond, just like the Baker's solution in one dimension. Okay, so Anderson was suggesting this for a triangular lattice and made some estimate for the ground state energy that was actually quite good. But I think later people were doing using quantum Monte Carlo and high temperature expansion and so on. And it turns out that for Heisenberg model, there is a way of relieving this frustration because this frustration was actually, the picture was for Ising spin, just like that. But this is a Heisenberg spin, so they could compromise by pointing 120 degrees to each other. So each one would enjoy a little bit right, of the even classically would enjoy some of the anti-ferromagnetic energy. So it is not truly frustrated in that sense. You can have a compromise. And so I think now it's established pretty much this is the true ground state. With a very much reduced moment, the ordered moment is much smaller than the classical Bohr magneton. I forgot what the number is. So it barely made it. So again, once again, triumphs. Yeah, but and as I was now, so this still kind of was kind of forgotten for a number of years. Not too many people pay attention to it since that time. Yeah.
How different is the energy in this 120 degree state from what you would estimate classically just by multiplying the?
Oh, I think it's very different, but I don't know the numbers. But the ordered moment end up being very small.
Yeah.
Already with square lattice, the ordered moment is half of the classical one. So this, I don't know the numbers, probably like, I would guess like 20%. Yeah, so classically you don't do very well. Yeah. So the whole story was revived after the discovery of ITC because Anderson remembered this old paper and suggested that if you dope this, if you have a spin liquid and dope it, then you can get a superconductor. So this is a doping demonstration. You can create vacancies. The vacancies become mobile, and if the vacancies are coherent, then this becomes a superconductor. Because if you concentrate not on the vacancy but on the pair, then it's essentially it is a superposition of Cooper pairs. That's a very beautiful idea. And so that of course now some of the problems objection is that in high TC it is a square lattice, right? So and you started with an ordered state. It's very far removed from this resonating valence bond state. So why are we talking about RVB state when we're talking about square lattice? So the argument is that in the other state is very quickly killed by once you dope because as I demonstrated in my talk, once you have this dopant, if it runs around, it will totally scramble up your spin. And experimentally, 3% of holes is enough to destroy them. It's very strong in your orbit. Right? So the state that emerges after it has been killed by this hole is a very complicated beast, and we don't know how to begin to describe it. And so it's not crazy to think that some of these arguments, the idea may actually apply once you've scrambled up the spin. So you destroy the spin not by frustration, you destroy the air order not by frustration, but self-consistently by homomorphism. The question is, you end up with something, again, similar. So that's, of course, open, very much an open question.
So for this 120-degree phase, the only degeneracy that's left is global degeneracy,
Right.
right? There's
Those are
nothing,
the standard
yeah,
ideas.
there's nothing.
There's nothing interesting. Nothing special. Okay. Well, in the meantime, the theorists have been busy at work, and so there's been a lot of theoretical effort to study what are the properties of spin liquids if they exist, okay, and classify them. My friend Shagan has gone to great distance in classifying all possible spin liquids, all possible. Wow. And I think after 20 years of work, people have a pretty good idea. I think people have a pretty good understanding of what might happen, or what we can expect to happen. Okay. So the interesting pictures that we have is that these spin liquids originally defined as just the absence of order. Right? If that's all that it is, not very interesting. It's just not an order. But I think we understand now that you cannot just do it, just not order in a boring way. Right? So when that happens, we expect that there could be all kinds of interesting low-energy excitation that shows up, that the low-energy excitation would be unconventional. So for example, the excitation may be spin 1/2 particles. We call them spin-ons. In the air order state, the low-energy excitation are spin 1, because the lowest energy excitation you can do is to flip the spin, right? Turn it down to the up spin. That's a spin 1 excitation. And that object then you can translate, and that forms a spin wave or magnon. Okay. But that magnon carries spin 1, this is spin 1 excitation. So there are no spin 1/2 excitation in the classical, in an environment. Yeah.
These sudden excitation, do you think they obey fraction statistics, like the one I mentioned?
Okay, I mean, I think the statistics that people talked about so far, they could sometimes be fermions, they can be fermions, sometimes they can be bosons. I think, well, in special cases, if you break time reversal symmetry, people have discussed the possibility of any other. But I think the examples we have so far do not break time reversal symmetry. So that's why we don't, so far we don't talk much about it. But in principle, it's good.
Patrick, can you say, so I know concrete realizations or implementations of trying to construct spin liquids using some slave prescription or, and then with gauge fields, certainly spin 1/2 particles emerge and gauge fields emerge. But is there some more general, implementation-free arguments for why, you should get, let's say spin 1/2 particle, you should get gauge field?
No, I'm not aware of it. Just all the examples we know of.
Well, like you alluded to, so it's absence of order, but somehow it doesn't, you can't argue that it implies.
Yeah, as far as I know, there's no theorem that says that when you have absence of order, you have to have spin 1/2 particles. Right. And the other interesting things are that there will be emergent gauge fields. So, I think all of us agree that if these objects exist, it will be very, very interesting. And unfortunately, for many years, people have been toiling in this vacuum, and there are no experimental systems that can be studied. As I said, all efforts to find it, to defeat the AL basically fail. Somehow things always find a way to order. And it's only until a few years ago, 4 or 5 years ago now, that we finally have several examples of this video. So that's what I want to discuss with you a little bit. So again, in high temperature superconductors, the ground state are all conventional. Okay, the ground state of high TC is either a superconductor or a Fermi liquid. If you overload, If you underdose, you get this complicated disordered phase that we don't want to talk about. And then you have an anti-ferromagnetic phase. So the ground state all conventional, nothing very interesting. So if there is some spin liquid physics, it will be hiding at some high temperature region in the pseudo gap phase or the strange metal phase somehow. And if you're always concerned with finite temperature, it's very hard to make any precise statement. You cannot say, you know, this is my, these are my energy gap, this is my quasi-particle, and so on. Everything is smeared by temperature. So I think this is part of the reason why these theories are so vague and ambiguous and very hard to convince people that it is correct. So that's why I think it's very useful to have a spin liquid. Here, now we have a ground state. You have a spin liquid ground state, and you can really study in detail, find out what the elementary excitations are, what are the physical properties, what are the correlation functions. So I think it's a very important development. So what are the requirements? So let me define the notion of spin liquid with a little bit of care. We require an insulator, okay, obviously, because otherwise any metal would be a spin liquid. We want to have odd number of electrons per unit cell, because absence of anti-ferromagnetic order. But another important requirement is that we want an odd number of electrons per unit cell. Why is that? One example is a leather. If you have a leather compound, right? This has two unit cell. This is a unit cell. Unit cell have two sites, so I have an even number of spins per unit cell. And this can form a ground state system, an array of singlets like this. And this, for my purpose, is a boring state. Okay? This is a gap for excitation, but I would not call this a spin liquid, okay? Because it doesn't have an odd number. The reason for this is that if I accept this as a spin liquid, then I can smoothly continue this to silicon, which is a smooth electron per unit cell, which has a singlet ground state. So that's why we make this condition. Okay. But in the literature, you will find that a lot of people do refer to these things as spin liquid. I think it is no. Okay.
Excuse me?
Yeah.
What does the honeycomb that is given to this definition?
Yeah, honeycomb. There, I guess you have some additional handle you can say. You don't break any rotational symmetry. So I guess maybe I should modify my description somehow. I don't know what my position is. But,
on the square lattice, for example, there's also arguments that a rotational symmetric square lattice with spin 1 can have such a simple feature as ground state.
Does it? Okay.
Well, there's some arguments that the square lattice with spin 1
Uh-huh.
can have this featureless ground state. If it doesn't break rotational symmetry, then even there, that would have some interesting.
That can be considered interesting.
Yeah, I don't have any
Okay.
precise state.
Yeah. So maybe this may be too restrictive, but for my purpose, let's do this. Because I'm not saying that the honeycomb non-order state may not have very interesting properties also. And it probably does. Yeah, so at least in the honeycomb case, it is not just putting down diamonds. Right? That would be valence one solid. So the other case we can talk about is valence one solid, where the singlets are frozen in place. So those typically break either translational symmetry or in this case rotation symmetry. Right, for the honeycomb. So we're sure that at least I was going to say experiments, but the fun Monte Carlo people assure us that this state does not break any rotation symmetry. Okay. So that's the introduction. Now let me begin with a little bit of theory to show you at least in one approach how these fancy fermions and gauge will show up. Okay. So let's start with the Heisenberg model. Theoretic Heisenberg model. And we introduce fictitious fermions, right, to represent the spin operator. Okay. So the spin carries spin index, but the very important thing is that they we impose this constraint of no observation. So on each site, there can be only one fermion, and this fermion, of course, can point spin up or spin down. Right. So that's a faithful representation of a spin operator, of the spin operator, because the only degrees that I have left is spin up or spin down. If I don't have this constraint, then I will have some either vacancy, so this will be spin 0 degrees of freedom, which is absent in the original. So that turns out to be the most important thing. Okay, so once you do this, turns out that there's a mathematical identity that you can rewrite this as I plot SJ, just in terms of four fermions. Not too surprising because each S is a Armenian fermion, so this is a plotting fermion, and then we can write it this way. So that was first done by, I think, by Pascal. And you notice that they come in two varieties. There's a term that is like a Hawking term from set I to set j, which conserves the spin index. And there's something that may look like a pairing term, right, where I have a pairing on nearest neighbor with opposite sign. So no charge fluctuation is allowed. By charge, I mean the number of fermions, right, is not allowed to fluctuate. So from this point of view, now this is a highly non-trivial problem, not just because the fermions are interacting, but because there's an infinite, there's a constraint, which another way of enforcing this constraint is to put an infinite U, for example. So from this point on up to now, there are two ways to proceed. One way is numerical, and a way that has been very useful in my opinion, but also rather uncontrolled, is the whole notion of projected wave function. Okay. So what this is that you try to solve this problem with some kind of mean field theory. Right? First you ignore this constraint and try to solve this in some mean field theory, which you know how to do. You need some kind of mean field decoupling, look for some mean field state. And so we can write down some mean field ground state. So this state can have the L order, it can have pairing, it can have nothing, it may be a Fermi C. So this can have anything you want. And we apply this so-called good-square projection. What this does is to just take this wave function and by hand remove all states that violate the constraint. So this is an initial position of many states. But if I throw out all the components that violate this, and I'm left with something that does satisfy the constraint. Okay, so this actually qualifies as a spin wave function. Even though it started out with a fermion wave function, after projection it becomes a spin wave function. Okay, so it's a very drastic step, right? But I can use it as a trial wave function. It's variational, so it is a guess of what the wave function might be. And it turns out that there are very efficient quantum Monte-Carlo schemes you can do to calculate with these trial functions. The most important is that there is no Fermion sign problem. So that's the most important feature of this trial, this variational approach. Okay, so so that's just one avenue. If you start from this, then there are other, there are various kind of approximate scheme based on this called approximation and so on and so forth, where instead of doing an honest projection, you start sort of modifying your mean field theory. And those have also enjoyed quite a bit of success. Okay. Because now we're hopeful that with all these new developments of tensor product states, we will have a much richer variety of trial wave functions. But those are still in the pipeline, as I understand. Now you're all experts. You can go home and start creating new wave functions. Okay. But up to now, I think most of the if there are numerical work on these subjects and making difference.
How many parameters do these wave functions typically have?
Depends on who you are. Yeah, if you're not professional like me, we have very few parameters. But there are professionals who put, tens or hundreds of parameters.
And how much do you lose for the Hilbert space allowed?
Hmm?
By choosing this kind of variational states, do you have an understanding of how much Hilbert space are you actually losing by projecting?
Well, I don't know how to answer that question. I mean, I don't think you're losing any basis. If anything,
You don't use
I don't think there's any basis. I can take any basis and project it.
But the question is, after projection, do you take really the projected, like really the states that will be generated by...
The exact, you mean, is it?
Yeah, by...
How close is the exact? Of course, nobody knows. But it's a legitimate part of the Hilbert space. Okay. And there are people who try to improve on this projected wave function. You can do some kind of called improved Lanczos method. You can hit this with the Hamiltonian once or twice to create more states. People have made improvements, but generally speaking, you don't buy too much. And as I will show you, in some cases, you do amazingly well with almost even no parameters. Yeah. So the other approach is analytic, and then invariably leads you to gauge theory, because fundamentally this is a problem of we have extended our Hilbert space, we have enlarged our Hilbert space, and so we have to project back to the physical Hilbert space. And so we're dealing with a problem with where we have many to one representation, and that's what gauge theory does. So let me show you a little bit detail how it works. But before I do that, let me raise the question: why I'm doing it with fermions? Right? So you can certainly do the same trick with bosons, right? That you can also write the spin with bosons here, and that's called a Schringer boson representation, a very well-known method. And so you can certainly develop that line. Okay? And people have done that. And you can also, again, do mean field theory based on this bosonic representation. And basically, the mean field theory will come out, you have two choices for your current state. One is that the boson will both condense, and that would correspond to an AL order state, if the boson condense. Or if the bosons are not condensed, then generically they will be gapped. Right? So bosons has only two fates in life. They're either gapped or they both condense. That we know. So I was kind of make the general remark that the bosonic representation is better for describing the AO state, the AO or the ground state, or some gap spin liquid phase. If you have a spin liquid and the excitations are gapped, right, then this is more promising. The fermionic excitation representation is actually, you have to work very hard to get back to an AL state, so that's actually its weakness. But you have opportunities of describing gapless states, because I can have a Fermi C, I can have many possibilities. Now, of course, in principle, all the starting points are equivalent. They're equally exact if you can push it to Zen without getting an approximation. But of course, in real life, we can always have to approximate, and approximation is usually along the line, making some mean field, some fluctuation. So we don't know from a priori which one is closer to the truth. So the question is which one is closer to the truth. Yeah.
I'm just curious why you're not so happy with using Fermionic ones for the gapped or anything else?
No, I'm not unhappy. Yeah.
Because I mean, people
Yeah,
just like.
people do that. Yeah, so the Fermi can, yeah, so I should have said Fermi, of course, also have gap states. And in fact, pairing is one way of getting gap states. And there are many gap, yeah.
But also, I mean, you're gonna hit this, you're gonna get this eventually, but just at this point, I wanted to ask, so in high TCs, if you think a pseudo gap is some kind of a, you know, finite temperature gap in liquid,
Yeah.
then from that perspective, you want something like 0.2 or possibly 1
No, well, the ITC, I would think, no, the spin liquid that people are thinking about are actually D waveform. So they actually are gapless. They will have no,
or gapless meaning has no,
there's no, right, because the pseudo gap, you know, has big gap,
I see, okay.
and there's some component that has nodes.
So it's some D wave instability
Some
of
D
these,
wave
of these fermions.
Yes, exactly. So that's one thing that people are thinking about. That comes very naturally. Okay, so of course we have no systematic way to tell ahead of time which way is better. So I follow Andy's prescription. Just do it. And hope for the best. Just do it, and with some experience, maybe we can see which is the right place. And so we always need to, that's why we always need to compare with the experiment. I think this kind of theory cannot be done in a vacuum. There's not enough internal check for you to know which way is better. Okay. Now, so as I'll point out, this spin liquid appears to be gapless. So we will proceed with this fermion. That's why I proceed with this fermion. Okay. So how do we do this? Well, the first step is that there's a constraint. So we can enforce that constraint with a Lagrange multiplier, right, in the action. We introduce this Lagrange multiplier, and if we integrate over this Lagrange multiplier, we exactly enforce the constraint. So then I have this action. In principle, I could put this bodic action in here. And now this form of the Lagrangian invites very obvious mean field decoupling, or if you want to be more fancy, I can write down Haber-Strathanovich decomposition in two channels. Right? One channel is the hopping-like term, right, which I'll call chi ij. So I denote this average of this quantity by chi ij will be a complex object, and we can imagine that as a nearest neighbor effective hopping for the spin-offs. This fermion starts out life as just some local object. There's no life of their own. They're just on each side. I introduce this fermion. But at the mean field level, then they start hopping around. Like this. Now, also I can have this decoupling of the pairing, so now this fermion can also pair. Okay. And so I can write down such a Haber-Strathanovich field, and I can look for the saddle point. So the saddle point would have a finite mean field, and I can consider fluctuations around the saddle point. Yeah.
Looks like this pairing term, it contains at least one more channel, sort of a triplet channel.
Oh, does it?
I don't know, looks familiar.
Well, it's up, down, minus, down, up.
No, but that, if I grab, fermions from two neighboring brackets.
If I do what?
Fj up, dagger, Fj down.
Fj?
Or white wave or triplet.
I think this is a signal. Because of the minus.
There is an expectation of Xi. Well, you could also just have an expectation for SI.
Yeah, there's a third channel which I didn't write down, which is a Nail
That's
channel.
what I'm talking about.
Yeah, there's a Nail channel which I didn't write down. That's the bias, right? The bias is that there's no Nail over it. Right. So actually, that is a conventional decoupling. The conventional decoupling is to take this and factorize SI dot SJ. Right?
Okay.
Right? So that's the channel I left out. So this is orthogonal to the conventional decoupling. Right? If I do that, of course, then it will order. We do that actually. For example, the projected wave function, you introduce some magnetic box, some spin order, and project that to get a number. Okay? Yeah, so there are three channels as usual in the exchange, R3 and pairing, and I'm keeping two of them. All right? So I find a saddle point, and then the saddle point would be mean field theory, okay? And then I consider fluctuation around the saddle points. Now, as usual, these are complex saddle points, so there will be an amplitude and a phase. Now, the amplitude would have a finite restoring energy, and they will be gapped. The fluctuation will be gapped. So I think I can safely ignore the amplitude fluctuation. So the important fluctuation is a phase fluctuation. Okay. So let me just approximate this by fixed amplitude, but then I keep track of the phase of this chi-j. So if you ignore this pairing for the moment, then this problem is exactly the problem of fermion hopping on with nearest neighbor hopping on the lattice, right, with a complex hopping matrix on it. And the phase plays a role of a gauge field. Or it will regenerate gauge field. So it's a lattice gauge problem. The phase becomes a compact gauge field, which I will call Aij, that lives on the link. And this Lagrange multiplier that I introduced becomes the time component of that gauge field, which lives in the time domain.
Is the density of the spin-ons fixed?
Yes, the average density has to be half filled, because I know on average I have to have one per unit step. So certainly on average it has to be fixed.
And this
Now, if you enforce the constraint exactly in the beginning, there's exactly one per site.
But the constraint says that up plus down should be 1.
Yeah, the number of up plus number of
It
down.
doesn't tell you how many ups you have and how many
That's
downs.
correct. So
So the relative density is controlled, or?
no, that will come out of the solution.
It is a free parameter.
Is it? Yeah. Mhm.
And it feels like this action actually should know how deep in what phase you are. But since you started
Not
with
this one. This is
Heisenberg-
assuming that you're deep.
that's because you started with this Heisenberg Hamiltonian, I have no information.
Yeah. A little bit later, I'll give you another formulation which is called slave rotor, which can describe how the
Not
moment.
correct.
Yeah, but there's no charge degrees of freedom here at all. But you can easily dress it up.
By the way, you don't seem to have a mean field that controls the chemical potential, I mean, of the relative difference.
No, there's an average chemical potential I have to set to get my average density, and that is the average. There's an average value of this.
Nice.
Okay. So I have to, the mean field has to be half filled. So now you can see that with very few steps, this problem becomes a compact U1 gauge field, a couple of fermions. So I think if this saddle point is anything close to the truth, I think so from going from that saddle point to this, I think it's quite legitimate, because all we are throwing out are these gap degrees of freedom and keeping the lower edge. Okay. Now, a very important thing to keep in mind is that now we think of this as a low energy Hamiltonian, right, where we integrated out gauge field. Maybe I should come back to that later. From the point of view of low energy Hamiltonian, then I don't want to go back to this constraint of exact 1 fermion per second. So now I liberate my fermions. Now they can run around. Right? Before they're frozen. But from the point of view of low energy physics, the fermions now they're free to run around. Right? All I ask them to do is to have an average. On average, there's 1 per site, and there's this gauge field to kind of keep them honest, right? So they still remember that they're not totally free. So this gauge field must play a very important role, because that's what distinguishes between free fermion. So, what is the physical meaning of this gauge field? Well, the gauge invariant object would be the equivalent of magnetic flux. So it's the curl of A, which means that if you hop around a plaquette, right, then you enclose some flux. Right? So you have some chi-ij with complex hopping, just like in conventional tight binding formulation, the Pyle's approximation. When you hop around, then that the phases add up, and in general can have a total flux. That flux is gauge invariant, right? Because there's a gauge should point out there's a gauge invariance and formulation, local gauge invariance, just like you're showing in the view. So I have this gauge invariant object. So the reason I have this gauge invariant object can be thought physically in the following way. If I take an instantaneous snapshot of my spin configuration, they will be pointing in some general direction, right? So this is supposed to be a three-dimensional picture of the spin. Right? So if I take, now a fermion hopping around this spin configuration, the fermion when it hops preserves spin, right? So you have to project the fermion to the local quantization axis when it hops. Okay? And that projection, when it hops, will pick up a Berry space. Because the spin has to hop with respect to the local quantization axis. And that Berry space this gauge field is our way of capturing that Berry space. Okay. So another way of saying this is that if I take these spins and put the tails at the center of the sphere and the head on the surface of the sphere, right? In general they will subtend a solid angle. Right? And that solid angle would be like a half of the solid angle would be the flux for this. Okay. And also very early on when Ruchek and Z showed that this flux is related to the notion of spin chirality. Spin chirality is S1 dot S2 plus S3. So you have three spins. So that's essentially, that is the solid angle subtended by three spins. That's spin chirality. It says to what extent these things are not planar. Okay, so they have to subtend a solid angle. So that is a measurement of this issue.
Can you explain again why the hopping fermions conserve the local spin?
Oh, because my chi-ij conserve the spin quantity. Alpha is
I
the
see.
spin quantity. So they hop just like conventional electrons. They don't change the space. That's the nature of this decoupling. Any questions?
So if I think about this 120-degree state,
Yeah.
so should I think of it as some crystalline state of fluxes, or?
No, but this one is flat, so this one doesn't.
Yeah, but I
have-
can still.
Yeah. So if they fluctuate, then there will be some fluxes associated with it. So people have actually studied. There are examples people have studied magnets that have this kind of flux, and the electrons traveling around it actually sees this.
But I think of that as a pi flux.
Yeah, that may be. Is it pi?
Well, because they're all on circumference.
Yeah.
On the equator.
On the equator, yeah.
I'm just wondering whether this description will give you some ordered version of,
Yeah, but it's
That's
ordered. Yeah, I doubt it.
You got it, okay.
Okay. Yeah. So we're gonna be talking about gauge field a lot later. But so gauge field sounds like a very abstract concept, but I think there is actually a very concrete relation to back to the physical spin. Because now we are in this strange space of fermions and the gauge field. But I think in fact this gauge flux is quite physical. So the fluctuation of this gauge flux is actually fluctuation of this chirality. So I think I hope I convinced you that the low energy Lagrangian of this problem, once you accept this mean field, this saddle point as a saddle point that is maybe close to the truth, right? Can be readily mapped to the problem of a compact gauge field coupled. It's compact because of the ability to become a lattice. Compact gauge field simply means that there's a 2 pi. I can make a 2 pi periodicity on my AIJ without changing. Okay. All right. So what are some of the saddle points that we've investigated that are popular? The simplest one is that chi-ij's are real and constant. Okay? So that just corresponds to fermion hopping tight binding model nearest neighbor. And that's familiar to you. At half filling, I would have a Fermi C. Okay? And the square lattice, that's a famous diamond. Okay? The square lattice. The Fermi surface half filled. Right? So for square lengths, I can put pi fluxes on my fluid plaquette, just as a trial wave function. So I'm allowed to do anything I want. So this one turns out to have these direct like spectrum, just like graphene. Now everybody knows graphene, so I don't need to explain this. Okay, so just like graphene, there are 4 minimum, band minimum. So this is a state which is gapless. Yeah, have these 4 points in the Brillouin zone, and out of this point will grow this Dirac cone spectrum, which I tried to right here. Another possibility that people investigate is so-called staggered flux space, where now I go from this and have a variational parameter, right, with different fluxes in a staggered pattern. It turns out that gives the same Dirac spectrum, but now it's flattened. This cone becomes anisotropic, just like a supernectar would, okay, with a pairing that is smaller than yeah. So these are the variety of states that people have investigated. So this is the mean field state. So now we have to couple this mean field to gauge fluctuations, right? So now we have gauge field and coupled to gauge fluctuation. Now, formally, this gauge fluctuation, this coupling is infinite. The coupling constant is infinite. Because the gauge fluctuation, the gauge field was initially introduced to as a way of enforcing the constraint. So there's no restoring force for the gauge field. Like if you look back at this effective Newtonian, the gauge field lives only on these on this hopping term. There's nothing that tells that constrain my gauge fluctuation. But I have to integrate over all lambda and over all aij, right, without any restoring force, right? So in usual electromagnetic problem, there is a f mu squared, right, over E squared, let's say, right? And this is what restrain the gauge fluctuation. So in the world we live in, E is very small, right? Pi structure class is very small, and that's why in the world we live in, the gauge field fluctuation is very small. I can see you, and it's not distorted by random gauge fluctuation. So that's proof that we are living in a recoupling world. Okay. Now in this world, people made up of fermions will not be able to see each other, because in this world, this term is not there, so this is infinite. So there's an infinitely strong coupled gauge field to start with. Okay. Now, by renormalization argument, you can say, oh, I can integrate out some of the high energy. I can start integrating out high energy excitation, and then I will start generating something like this. Okay. But the best you can hope for is to get a term where this gauge coupling is over 1. Okay. So I think we should think of this low energy field as a compact gauge field with coupling constant 1, or strong coupling. Okay. Then the question immediately comes, if you have a strong coupled gauge field, are you in the confined or deconfined? Or even weak coupling gauge field, for that matter. Okay. In fact, there are people who argue written papers saying that, oh, because you have infinitely coupled, you must be in the deconfined, you must be in the confined phase. And that is wrong. It's a wrong argument. We know examples where even if you start with infinite coupling, you can go to a deconfined phase. But so I think the enemy of spin liquid is confinement, because the valence gauge theory can be confining, and if it's confining, then these fermions that I introduced by hand would bind back together and form the excitations will be spin 1 excitations again, either singlet or triplet, and I get back the low energy excitation will be spin 1 boson, just like electromagnetic field. And in fact, the root is well known in particle physics. If I start with a high flux phase, I have this fermion with an SU2 gauge field, field, then there's chiral symmetry, chiral symmetry breaking, which in our language is exactly order. So this is the complicated route. If you start this way, there's a route of getting back Neo order by this complicated route of confinement. Now, our hope is that we somehow ended up in the deconfined phase. Okay, if this gauge fluctuation drives me to this confined phase, then I'm finished. Now is 1. But if there's a chance that this thing goes into a deconfined phase, then something interesting happens. Right? In the deconfined phase, that phase is smoothly connected to the world that we live in the sense of the electromagnetic field, which is, in other words, if the deconfined phase is smoothly connected to the weak phase. Okay. And in this world, fermions in gauge field emerge as elementary excitation, as new particles. Just like in our world, we are very comfortable with saying that electrons are particles, real particles, and electromagnetic fields are real particles. Okay. People often object that these fermions I introduced are fictitious, and they are not gauge invariant, right? Because there's a gauge symmetry. Right? I can, because the spin is written in terms of local fermions, I can make any local gauge transformation on the fermion. It doesn't change the spin, and therefore there's a totally arbitrary local gauge degrees of freedom. And people would say that if because of spin-ons are not if fermions are not gauge invariant, they cannot be a physical particle. Now that argument is totally wrong also, because the world we live in, electrons are not gauge invariant. Right? But we are perfectly happy to think of electrons as being real. This is very strange actually, right? Because I cannot even write down a Green's function for electrons, even though people think they measure them experimentally.
Well, you can pick a gauge.
You can pick a gauge, but that
You can pick a gauge.
you can pick a gauge, but that's not the legitimate thing to do usually, unless because your answer depends on the gauge you
So
pick.
you pick a gauge and then calculate gauge invariant
Yeah,
quantities.
that's what you should do. Yeah, but we don't do that usually. Right?
So you pick a gauge, compute, let's say,
Yeah, so
you compute the
That's
Green's
right.
function and look at the spectrum.
so
That's a gauge
that is the
invariant.
right approach, right? So for every physical measurement, we should compute physical measurements, of course, gauge invariant objects. So we should compute gauge invariant objects. But it doesn't mean that we have to abandon these fermionic degrees of freedom because they are the correct low-lying degrees of freedom. So the only difference with the world we live in is that because the gauge coupling is so small, we're used to thinking of electrons as almost free. And that's why we think of electrons as a physical object, because E is so small. But indeed, electrons are always surrounded by electric field and magnetic field. You cannot decouple them. Yeah.
So you're saying that this fine structure constant will turn out to be a order of 1 for this
Yeah.
theory?
Right.
What will the speed of light be?
Yeah, it will be, I'll have that on the next slide. It will be the exchange constant. Yeah, so it will be like, it will be 10 to the 6 centimeters per second, to be precise. It's like a Fermi velocity.
So it should be
Fermi velocity, it will be
the
something
same
else.
as because there's nothing else.
But there's no other scale.
Right.
Okay, so this is sometimes called fractionalization because I've taken a bosonic degrees of freedom, which is a spin, and fractionalized it into two fermions, a spin half fermion. Okay, so this is a marvelous example of this notion of emergence because in this theory I introduced totally fictitious objects, right? Just formalism to describe this local constraint. And at the end of the day, I claim that under the right circumstances, the law in the physics is described by these objects. So these objects that was formal in the beginning becomes real, takes on a life of its own. Right? And so we call these fermions and gauge field emergent particles. Okay. Now, they are not free. They are interacting by something of order 1. But their interaction does not lead us to they are not confined. Okay? And in fact, their interaction can lead to a new kind of critical state, which is not free at all. So this is, from this point of view, this is the route to getting a spin. So it's based a lot on some pious hope, right? That this deconfined phase can emerge. Yeah.
How do the gauge excitations, the monopoles, how do the monopoles look like on top of this pi flux state?
Monopoles.
And the excitation of the gauge field,
Yeah.
how do they look on top of this mean field state?
Yeah, they will be, right, there will be gauge fluctuation on top of the mean field state.
Well,
And initially, there will be a order one, right? So each, right, but
but what is the charge of this
it's
monopoles?
order one, right? So the fluctuation is as big as the mean field itself.
But are they magnetic or electric or?
They're both. Right. Just like our world, there's electric field fluctuation. But I'll go on and talk more. Okay. Yeah. So this leads naturally to a number of theories, and so now we know several examples of these kind of theories with gauge field. Okay, so there are basically two kinds. One is the U1 gauge theory. So the examples I've given you a so-called U1 gauge theory because the gauge field are U1. Okay. So there will be gapless direct. There's either Fermi C in this case, or there will be gapless direct spin-on that are coupled to U1 gauge field, which is indistinguishable from the electromagnetic field. And actually, there have been several exactly soluble examples of these spin liquid phase, starting with a microscopic Hamiltonian by Kitaev, first by Kitaev, and then Wen. These generally have finite energy gap, and they go under the Z2 gauge theory, which I can imagine as starting with U1 and breaking the U1 symmetry. For example, by pairing. In the conventional superconductor, right, superconductor breaks gauge symmetry, right, because the autoparameter break gauge symmetry, but it breaks down only to U1 because if I have a pairing autoparameter, this is true also for conventional superconductor. Right? So this is my autoparameter, but I can change the sign. The U1 gauge symmetry means I can change the phase of the electron operator, right? And nothing changes. But here, once I have this autoparameter, I can still change the sign. Right? So there's a discrete symmetry, and that's the Z2 symmetry.
But so, at least what you have done so far, if your F's don't pair, you have a U1 gauge.
That's correct. Yeah.
So, can you just elaborate a little bit on that next step to get to the Z2 gauge theory? Is it, you're saying
One route of getting there is for Fermions to pair, but presumably there are other routes too. Right. And I'm just saying that there are exact solutions that has this kind of gauge Z2 symmetry. What else do you
well,
want?
I'm just trying to understand whether it's a different description of the same thing, or it's two different states. I guess it's two different physical states.
They could be, even within the Z2 gauge, there are also different states. Yeah, there are many possible spin liquids. Right? I think Shotgun has one, 200. Yeah, there are lots, yeah, but Shotgun 1 is classified. Then basically by going to the different mean field decoupling, you can write down and carefully keeping track of the gauge transformation, gauge rotation. They classify what's possible. So these are not full, just saying that something is U1 or Z2 is not the full classification. There are many more sub-classifications. They may be gapless, they may have nodes, point nodes. The point node may live anywhere in the zone. There may be 4 nodes, maybe 2 nodes, right? So those are all the different possibilities. Like there's gap, maybe not gap. So there are many, many possible states. Right? So nature has plenty of opportunity to make us happy.
I guess I just don't understand that. So, U1 gauge theory is there because spin is made up of C dagger C.
That's right.
But how do you ever break that if your physical degree of freedom is spin?
So, well, it's all has to do with emergence. Yeah. By low energy, by the time you get to this low energy Hamiltonian, you can, all kinds of things can happen. Yeah. Yeah, because these fermions are not physical to begin with, so I can do anything with them I like. Okay. Now, there actually has been some progress, important progress, to address this question of whether we have deconfinement or confinement. Yeah.
In the U1 gauge theory, the correlation in parallel decay.
It doesn't have to be. Yeah.
And then
Depends on whether it's gap or gapless.
zero gauge theory. I know today if the correlation is
gap.
a short range, it's only
Yeah. Right.
in the
Yeah.
flux. But it's not necessary for U1 gauge theory parallel decay.
Right. So I think both these, or if there is a Fermi C, then typically you have parallel decay. If it's gapless, it's parallel. And so that's actually this algebraic spin liquid. So that actually has been some progress about this issue of confinement and deconfinement. Let's see. Yeah, so there's a paper by Mike Hermley, who's here, several years ago, who showed that deconfinement is possible if the number in this kind of flux space, in this kind of pi flux space, if the number of fermions species is large. So here, in the physical example, there are 4 component fermions. There's 2 spin, each node is 2 spin, 2 nodes, just like graphene. So the n should be 4 in this example. What he can prove is that if n is large enough, then this thing will be deconfined. And very recently, Sung-Sik Lee has a paper in this, like last year, which showed that the Fermi surface coupled to the U1 gauge theory, according to him, is always deconfined, no matter how many components you have. Generally speaking, the more low energy, okay, the notion of confinement came from this paper by Polyakov, which was a description of the pure gauge. If you only have gauge field, nothing else, no fermion, then we know that in 2 dimensions it's always confined. But matter field, if you introduce fermion, that can change the equation. So generally, if you have matter field, you have additional low, if they're gapless, then you have additional low energy fluctuation, and that can ruin this Polyakov argument. So this Polyakov mechanism for deconfinement is by creation of instantons, which changes the flux by 2 pi. And so all these arguments says that that is not possible. Yeah.
The spin carry charge, right?
I'm sorry?
The spin carry charge. Right?
Not electromagnetic charge. They carry gauge charge.
Yeah, yeah. So if you see we have now spin liquid, as in the experiment, they measure the spin surface, this spin from surface. Do you think that's possible?
Yeah, I'll get to that eventually.
Can you read out the rest of things you find that you can find from the relational wave function?
No, I don't think so. Yeah,
Is there a way to couple to the gauge charge somehow?
yeah, I'll get to all that. Yeah, but you have to be here tomorrow. I'm afraid no one will be here tomorrow. Yeah,
Is sunset result controversial or is it?
that I don't know. His argument is a many patch argument. So he's just saying that many patch is the same as large n. That's basically the argument, which seems reasonable because Fermi surface has huge amount of low energy. So one Fermi surface is probably as good as a zillion of these erratic nodes. But that's my simple-minded way of understanding it. It seems reasonable. I don't know if people have gone through that with the fine code.
Does he
Maybe you should.
allow, does he allow all kinds of scattering on the Fermi surface, or does he allow only forward?
No, he argued that it's patch. He has a patch picture. So he argues that the important scattering only forward.
Only forward.
And that is the case for a couple of the gauge vectors you see. So, going back to your question about fluctuation, confinement means that there are huge gauge fluctuation. Right? So this instanton means that usually in the world that we live in, there are no monopoles. So if you integrate the magnetic flux over the world is conserved. Right? But in the confined phase, this instanton, once the instanton pops up, that means that the gauge flux has changed by 2 pi. So this total gauge flux of this world is actually fluctuating wildly. And that's what's responsible for So the notion of deconfinement is that yes, there is a loss of gauge fluctuation, but the total flux is still conserved. So that is the concise or the crisp statement about confinement versus deconfinement in the presence of matter field, is that the total flux is conserved, doesn't change. Okay, so now the long-awaited examples. There are 3 examples that we know of, and so let me first concentrate on the organic material. I think you've seen this before, but I'm sure you've forgotten it by now. So let me show it to you again. Yeah, so there's a class of organic materials called ET is a shorthand for this not too complicated organic molecules, right? Sulfur and carbon and so forth. A kappa denotes the structure of this arrangement of these things. It turns out that they arrange themselves into layers, right? And between the layers are these X, which are another kind of molecule. So this is like organic charge transfer material. So these are responsible for donating charges to the organic layer. And the nice thing about organics is that you have a huge flexibility in playing with these donuts. You can replace them with different things and change the physical properties. Now, these ET2 means that these molecules occur in diamond, so there are pairs of them. Right? So you should think of this as molecule. And each molecule, think of it, if you think of each molecule as one unit, then if you look from the top, they actually form a kind of a distorted triangular lattice. If you look from the top, then these 2 molecules form one unit. And that forms a kind of triangular lattice.
So each one I should think of as ET?
Each one is ET2. No, each one is ET, and the pair is ET2.
Okay, each one is ET.
So this would be my unit cell. Okay. And it's my unit cell because if you do the charge counting, this guy turns out to have 1 electron per molecule for ET2. So there's 1 electron per site. Okay. So the minimal model would be a Hubbard model on a triangular lattice with 1 spin and a half.
So what's happening? The road, you have these.
There's some tilting in the plane and so.
No, but what I mean is, one is kind of has hexagons facing you, and the other one's flat.
Yeah,
Are
so
those the same?
they're facing, they're changing, right? They form this kind of.
But those units in 3 units, they're identical units.
Yeah.
On the left,
Yeah.
those are that guy and the next one too. That's identical. They're identical. They're oriented differently.
Yeah. And so each of these 2 is a pair. There are 2 of them.
I see.
Okay.
What's the scale of the Hubbard U?
Don't know, but the interesting thing about this is that you can drive the screw Mach transition with pressure very easily. So these things can be tuned to be very close to the Mach transition. So generally, as a rule of thumb, the hopping energy is a factor of 10 smaller than the in metals. Right. All energy scales are a factor of 10 lower.
And
So
U also is.
you presumably will be
Therefore
factor of 10.
moderate.
Yeah.
Yeah.
You know, instead of 4 EV, it will be half of EV, or even less. Because we know that we're in the vicinity of the okay. Now, one thing you can change is to change the anisotropy. Right? So the structure actually is a squash triangle. So there's a P prime hopping term and the P term. And yeah, so by tuning this X, you can change the anisotropy. This is based on quantum chemistry type calculation. It's not theoretical. It's not experimentally determined. And so there are several examples that I want to talk about. For example, if this anisotropy is 0.75, then okay. So many of these are actually superconductors at ambient pressure. And the examples I want to talk about are actually insulators. So they happen to be there on the Mach side, on insulators on Mach transition. So this is the estimated value of U over T. But the interesting thing is that I can tune in the experimental thing that I can tune in anisotropy If it is isotropic, if it's anisotropic, you have the more or less conventional phase diagram. So this is one where the P prime is anisotropic. At ambient pressure, you have a Mott insulator, and there's an anti-ferromagnetic order that then goes away by low temperature. With pressure, amazingly, it turns into a superconductor. This is the highest transition temperature superconductor we know for organics, 12 degrees. And as I would try to argue, is that 12 degrees for an organic is the same as 120 degrees for metal. So this is actually a ITC superconductor. Okay, now the interesting thing is that if you go to this guy, where you're supposed to go to this more isotropic triangular lattice, then this anti-ferromagnetic disappears. Right? So you start with an insulator, which doesn't order. So this is our friend, the spin liquid.
What's preventing the 3 sublattice ordering?
Yeah, we'll come to that. Because the short answer is that because we're quite close to this one. So this problem cannot be described by Heisenberg model. So now interestingly, under pressure, this guy also becomes a superconductor. But this is only a 3.5 degrees superconductor, not the 12 degrees superconductor. Just a random fact. Okay. People have looked for nail ordering with NMR, and there's no sign of ordering down to milli-Kelvin scale. Now, the exchange is believed to be about 250 Kelvin, quite large. Again, because we're near Mach. Right? Remember, exchange is T squared over U. The closer you're to Mach, the bigger the exchange will be. So again, for 250 Kelvin is like 2,500 degrees for Cooper. This is very, very big exchange. Now, the exciting properties are that, first of all, the magnetic susceptibility takes this form, and in fact, by fitting this to theory or Curie-wise is how you extract this J exchange constant. By high temperature series expansion. At low temperature, it comes down, and the important thing is that it comes down to a constant. It doesn't go to 0. If there's a spin gap, if this goes to a spin gap phase, then it would have gone down to 0 with an activation. This thing goes to a constant. So that's the first hint of something interesting. And consistently, the night shift also goes to a constant. One of the T1T I'll talk about later. So there's a finite susceptibility. That means that there's an abundant low energy excitation at the low temperature. Now, the important observation is the specific heat measurement by Akazawa. This is out of date. This slide is very old. Actually, it already came out 2 years ago. And so they do the specific heat, but the standard part of T squared kind of comes down like this. This is quite high. This is T squared, so this is about 6 Kelvin. If you zero in at the low temperature scale, between like half a Kelvin to 2 Kelvin, you find this straight line. The important thing is that they extrapolate to a finite value. So this is how experimentalists usually determine the specific heat gamma, the linear term in the specific heat. Okay. And it turns out to be about 15 millijoule per Kelvin per mole. Okay. Now, this is the kind of thing you expect for metal. Right? We're familiar with something with a Fermi C. But for an insulator, you almost never see this. Right? Insulators would never have a linear gamma. So this is very unique. It's the cause of all our excitement. Furthermore, so now of course you see where I'm leading to, right? That this guy is there's some Fermi surface left here, right? Looks like this is consistent with Fermi surface. So another test of Fermi liquid is that there's this thing called a Wilson ratio. Right? In free fermion, you can work out the ratio of the spin susceptibility to the specific heat gamma. Right? There's a fixed ratio. That's called a Wilson ratio. If you work this out here, using the data on the last slide, you get something very close to 1. So it's all behaving almost like a free fermion, as far as the spin susceptibility and the specific heat goes. Yeah.
What is the nature of the change of the slope at 30 Kelvin?
You mean this guy?
Yeah, the change slope.
Yeah, you have good eyes. Yeah. So, yeah. So this is actually very interesting and not well understood. The experimentalists made a subtraction, kind of background subtraction. You can see that here's very good eye. So there's this kink, kind of a kink here. Right? If you make a subtraction, it looks like there's a peak in the specific heat. Right? At around 6 Kelvin. Right? This is T squared, right? The kink happens at 40 at T squared, so it's happening at 6 Kelvin. So there seems to be, and this linear T is down here. The gamma is down here. There seems to be a big peak here, right? If you use your imagination, you may even think this is like a BCS pairing peak. Right? So for some time we were thinking this may be a pairing transition, but now we have some doubt. Anyway, there is a phase transition here. And this transition has been confirmed by very careful thermal expansion, which is very sensitive to phase transition. So we know, I mean, this depends on subtraction and so on. So dicey, but we know that this is a real transition. So that's one of the open questions that we address. Yeah.
What about thermal transport of these points?
Oh, yeah. Okay. Can I go? Yeah.
Yeah.
Yeah. So very recently, another example has been reported, and that is so for a long time we only have one example, but people have another material instead of ET. The shorthand is DMIT, which is very easy for me to remember. So this material again sits. So usually they would have an AO order, but this particular one, again, they think they can tune this anisotropy. When it's isotropic, then it doesn't order. Okay. So again, there's no sign of order down to lowest temperature. This is known from 2 years ago. And again, they show the same kind of specific heat, same kind of indiscriminate heat. So we have two materials that behave like a Fermi surface. And the size of this gamma is pretty much the same. Now, so in the literature a few years ago, there was some proposed explanation. Well, maybe you have localized states, right? Suppose your states are all localized. Then I have a finite density of states at the Fermi level, and then you can give rise to some localized conventional electron states. An insulator with localized state may give you some kind of a finite density of states. But I think this can be ruled out because if you figure out what the resistivity is, anyway, but I think the most convincing way to rule this out is, as Leo suggested, we can do thermal transformation. Right? So these guys, if they are spin-ons, they carry spin. Right? But transport of spin is very hard to measure. Spin transport is not an easy experiment. But these objects should carry entropy. Just like each one has spin degrees of freedom, so they carry log 2 entropy. And so they could transport heat, just like conventional metal. Right? So these are real spin-ons, they should conduct heat like conventional metal. And indeed they do. So this is a very recent experiment, just came out, I think, 2 weeks ago in Science. Let me first focus on this DMIT material. And so the conventional plot, again, is kappa over T versus T squared. So this is the usual plot you plot for phonons. So what is found is that this thing extrapolates to a finite, is linear, and extrapolates to a finite value. That means that at low temperature, that there is indeed thermal transport. Remember Wiedemann-Franz law, kappa over T is like a conductivity. So here we should think of kappa over T as a measure of the spin conductivity. Okay? So this is evidence then that the spin conductivity is in fact finite. And in fact, you can use the formula from Ashcroft and Merman, which says that the thermal conductivity is the specific heat times the Fermi velocity times the mean free path, and extract the mean free path. This mean free path comes out to be half a micron, which is 500 times the interspin spacing. So this spin-on is traveling freely, right? Carrying a huge amount of heat. This is a very large number for thermal transport. Okay, so I think now we have evidence then that we have mobile objects that are fermionic, that are living in this insulator, right? That are gapless. So what else can it be other than some kind of gapless fermionic Fermi sea, or parts of it, or pieces of a Fermi sea or something? So that's the cause of great excitement. I'm running out of time, so there's a lot more I want to say about this experiment. Let me continue tomorrow morning, if you're still here, and show you more. And then I will go more into the theory of how do you understand questions of why, how do you escape.